Okay, first thing I want you to do is let's do a little bit of practice. We'll get to those 3 theorems, but a little bit more to brush up from what we did yesterday. I don't think we did one exactly like this. Maybe we did out of the book. But let's have you use slope to determine whether this triangle is a right triangle. If so, which angle is the right angle? Use slope. How's slope going to help you? What can slope tell you? Do you see how slope can be used on this problem? Okay, what can you determine from slopes? Parallel or perpendicular? For a right triangle, you have to have perpendicular, because that would mean there's a right angle, which makes a right triangle. Okay, so you need to calculate the slope of each side of the triangle, which would be KL, LM, and KM. And we're going to compare them to see if any indicate that there's perpendiculars going on. Take them, find slopes. So we get the slopes. You got all 3 slopes? You gotta watch your positives and negatives real careful, because that does make the difference between the answer. You goof up, it could mean that they're not parallel, or that they are, or that they're perpendicular, or they're not. Makes a difference. Okay. Are you finding any slopes that are opposite reciprocal numbers? Yes? Which ones?
KL and
KL and MK? Was it 3/4? Or was it negative 3/4? Negative 3/4 and positive 4/3? Okay, so those two are the perpendiculars. Look at the names of those 2 segments. Where they meet would be the right angle. Which one's the right angle? Okay. Correct. So K is where the right angle is at. All right, how about writing equations of lines? These are basically the 4 type. If I gave you some before this, it would be really easy ones. So let's see if we can run through these before we get our theorems. Through those 2 points, can you write the equation of the line? I want it to end up in slope-intercept form. So this is reviewing some of what we did yesterday. The equation of the line that goes through those 2 points. Remember, you need to figure out a point for it to go through. You've got 2 choices on the first one. And then the slope that it needs to have. You've got to figure that out. change the slope? No, don't have to change it. We're not looking for anything perpendicular, we're looking for the one that really goes through there. Everything's slope intersect. If you're waiting, you can go on to like the next one, but keep your answer to number one. And I'm sure that you'll be able to check it. First one was y equals negative 5x plus 27. Okay, second one. Through the point 4, negative 8 and parallel to that line. Remember, you need to come up with a point and a slope, and I'm even going to let you keep that one in point slope form, it says. Figuring out the slope to use. Keep the same slope or do you change it? On number 2 with point slope. Okay, number 2, point slope. Y plus 8 equals negative 2/3 parenthesis x minus 4. X minus 4 because the point we want to go through. A question on number 2. No? Okay, 3. Number 3 carefully. Number 3. Okay, did you have to do something fancy on the slope? Yes, because we needed perpendicular. About y plus 1 equals negative 1/3 parenthesis x plus 4. Okay, last one. Perpendicular bisector of the segment that has those endpoints. Now, thank God, you got 2 things, what point and what slope. plus 1/3.
Negative 8 divided by 2. No. Negative 10 plus negative 5 is 2. Because if you're saying negative 3 minus 5, then
What's
it has to
halfway
be
between -5 and
negative plus negative 5 is 1. Hold on.
Okay, so you're finding the midpoint and see if the x that you came up with is halfway between -5 and +3. Is the y in the midpoint halfway between 0 and 6? You really just stop and think rather than compute and go on. If you think about what you just found, you can maybe catch some errors once in a while. And slope, found the slope and then made it into a perpendicular slope. Got a mistake there, huh? All right, ready? The suspense is killing me. What is it? Y minus 3 equals -1/3 x plus 4.
I got it.
The sign's on. Okay, so your slope intercept is y minus the y value. Y minus x minus
Well, the slope, that's why.
what do you do? 6 over -2. Okay, so did you do something wrong? You went 0
Well, I
minus
forgot.
Okay, if you did 6 minus 0, you would go 3 minus negative. Or make it positive. You gotta go in the same order. Okay, any more discussion on those? Nope, somebody got that last one right before I showed you. The lower half. Okay. All right, let's finish up the part of the chapter. I think we got a little bit on that page 3-4. We previously discussed perpendicular bisector. That was yesterday, right? Okay. And we constructed the perpendicular bisector. We did that. Okay, I think we're ready for distance. Up the top of that page. Distance from a point to a line. It says that the shortest segment from a point to a line is perpendicular to the line. This fact is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. So in other words, if I gave you this and said, okay, measure for me, how far is point P from that line? Would it be okay for you to lay your ruler and measure this length? No? Measure this length? Measure this length? No? Where should I measure to get the point, the distance that point is from the line? See how there's a lot of different possibilities unless we decide what we really want? Okay, the distance is supposed to be the shortest distance. So when I measure here, where's it going to be the shortest? Okay, perpendicular, and that one doesn't look maybe too perpendicular. I know, I'd have to get my straight edge out and measure where there's a 90. Okay, I think I drew it in. It was there. So the distance from a point to a line, you might add a little picture to your definition there, is the length of the perpendicular. So from the point, it has to be perpendicular to the line. So they give you some, I think, kind of strange questions, but here's the type of question that they'll ask related to that. It says, name the shortest segment from point A to line BC. So in this picture, what's the shortest segment from point A to line BC? Is it AC, AP, or AB? AP. Okay. So don't say something like it's PC. Well, that doesn't go to point A at all. So AP is the shortest because it's along the perpendicular. Okay, that's all that part is. Write and solve an inequality for x. What's an inequality? Okay, not equal, so greater thans or less thans, correct. Okay, so involving x. So x is here, x minus 8. X minus 8, the only thing to compare it to would be 12. Is x minus 8 bigger or smaller than 12?
Bigger.
Bigger because the 12 is the shortest distance. So you could either go x minus 8 is greater than 12 or 12 is less than x minus 8. Either one of those is an inequality. So I did x minus 8 is greater than 12. How do I solve that? Just like if it wasn't equal, would you add 8 to each side? Okay. Addition property of inequalities, I guess. Okay, so we get x is greater than 20. So any number that's greater than 20 would make CA longer than 12. If you had the less than, you might end up with 20 is less than x. And I would say let's put the variable on the left side still. So let's see if you can do that on another sample. Okay, on your own practice, name the shortest segment from point A to line BC and then write and solve an inequality. Either just on your paper or on your marker board. It's not a real long problem. Shortest segment, Chase? Okay, from A to B, correct. AC is longer. Write and solve an inequality. What inequality did you use? Okay. X minus 5 is less than 12. Okay, any others? Everybody agree with that one? And when you solved it, what did you get? Correct. X is less than 17. Do you remember anything you have to watch for when you're solving inequalities? Okay, dividing by a negative or multiplying by a negative on each side, you have to reverse, flip that inequality sign. And what you could think of, if that really doesn't make any sense, when you go from the positive part of the number line, if you multiply all those by -1, don't they flip backwards on the other side of the number line? Everything reverses. So you have to turn the inequality because it also reverses. Okay, and we did that construction with the point to the line. Okay, here's your 3 theorems. Not all of them had titles in our book, but I found this title in a different textbook. So the first one was called the congruent linear pair theorem. Our book will probably just call it Theorem 341, but we can learn that name if we want to. Okay, the hypothesis. Look to see what you're drawing, or some of you maybe are just writing it out. Maybe it works better in words. It says you have 2 intersecting lines forming a linear pair of congruent angles. So 2 lines that intersect. They're saying these 2 linear pair angles are also congruent. That's your hypothesis situation. So what can you come up with if you know those 2 angles are congruent and they make a linear pair? They're right angles, they're both 90. Would that mean that L and M are perpendicular? Those lines would be perpendicular as a result. There's a few thinking steps in between there if we were proving it, but we can get to the fact that those would be perpendicular. Okay, how about perpendicular transversal theorem? In a plane, so it all has to stay flat, otherwise this could produce skew lines instead. But if it's flat in a plane, if a transversal is perpendicular to one of 2 parallel lines, so in your hypothesis you have to have parallel lines, got the arrows on them, You have to have a transversal, which is Q in this picture. Q is perpendicular to one of the parallels. So it's perpendicular to N. All of that's given. You have to have one set of parallels and one perpendicular involved. Okay, now, as a result, they said we can come up with Q and P being perpendicular. Can you talk me through how we would get to that? How would you really end up with, starting with this, how do you get Q and P being perpendicular? Haley? Corresponding angles converse or not? Are the lines parallel or are we getting them parallel? They are, so it's not the converse. Okay, so corresponding angle postulate, this 90-degree angle would also be 90 degrees down here, and that would be your perpendicular. Okay. Did you get the assignment? Okay, we'll come back and get it. All right, so if that was 90, this is 90 because of the parallels, and if that one's 90, we have perpendicular lines at the bottom of that picture. The last one is the dual perpendiculars theorem. Do you know what that word means? Two. There's a different spelling of dual, like fighting duel is D-U-E-L, so this is D-U-A-L. Two. So there's two perpendiculars involved here. The theorem's hypothesis says if two coplanar lines, again it's flat, they're just coplanar, they're perpendicular to the same line. So T and R are perpendicular, T and S are perpendicular. It says those two lines, in this case R and S, end up parallel. How do we convince that or prove that? Daniel? Okay, converse of corresponding angle postulate. If you've got these two angles that are both 90 in the picture, that would make the lines parallel by the converse. But it's a special case of the converse. If you're using it in a proof, you wouldn't have to go through the 90-degree angles, right angles, blah, blah, blah. You could just stick with the fact that they were perpendicular. So it makes it a little bit easier. Where would you ever use this? Here's a situation. Carpenter's square forms a right angle. If you don't know what a Carpenter's square is, can you see the little device that they've got pictured here? That's a Carpenter's square. Places it on the square so that one side's parallel to an edge of the board, draws a line along the other side, so lines up this part, draws this line here, then slides the square to the right, draws a second line. Why would the two lines that were drawn be parallel? Look at those theorems. What is this an example of? Look up the theorems that we just, right angle theorem is not one of those. Okay, dual perpendiculars theorem. You have two lines that are both perpendicular to the same line. So those two lines end up parallel. Now the right angle congruence theorem, is that what you were saying, Malia? Were you saying right angle congruence theorem or something? Okay, those are here's the transversal. Okay. So we've got a perpendicular there, we've got a perpendicular there. So we've got two lines that are perpendicular to the same line. So those two lines end up parallel. Converse of, you could. If you were doing that, you would have to do more than just perpendicular. You'd have to say, okay, yes, they drew it perpendicular. Perpendicular means it's a right angle. That means that it's 90. You have to do that twice, and then come up with it from that. So this gets a little quicker, but yes, you could get there. All right, let's do an actual proof. Let's put it on your homework also, or I mean on your notes. So either to the side of those constructions or the back side of the page. Let's write down a proof that involves one of these new theorems. A two-column proof. We are given R and S parallel and angle 1 congruent to angle 2, we're trying to get R and T perpendicular. We are going to use one of these new theorems. Which ones conclude that two lines are perpendicular? Is it all three of them? Do all three of them come up with perpendiculars? No, the third one doesn't, right? So we can't use the third one to do what we're trying to do. So we're going to involve one of those first two, or maybe both of those in this proof. Okay. What can we come up with? I'm going to erase that marking. What can we come up with from R and S being parallel that was given? Looking at what they've numbered as far as angles they think we'll use, what can you come up with? 2 and 3 are congruent? Why? Let me, you're just rambling. Okay. Are the lines parallel already? Yes, so it's the postulate, it's not the converse. So what Daniel was saying is, if we know R and S are parallel, which we do, we can get angle 2 congruent to angle 3 because of the corresponding angle postulate. Okay, so we just got angle 2 congruent to 3. Okay, notice in the given, angle 1 is congruent to angle 2. Angle 1 is congruent to 2. 2 is already marked that way, so 1 has to be marked the same. Okay. What can we come up with combining those two lines? We'll eventually use that. We need to state, before we can use that, we've got to state that they're congruent. So, angle 1 is congruent to angle 3. You know the reason, Isabel. Very good. Transitive property of congruence. Now we have what Lena needs. We have angle 1 congruent to 3, and they are congruent linear pairs. So you wanted to use the congruent linear pair theorem? Was that the first one or second one? First one? Congruent linear pair theorem, which was 3, 4, 1,
Yeah.
if you wanted the number. And what can we conclude? What's the conclusion of that theorem? In this case, R is perpendicular to T. So that's an example using the theorems of today. All right, that's where we got to in second period, so I'll stop there here also. And if you want to do the constructions on the homework before you leave, then you wouldn't have to drag along some tools. So here's what the assignment is. Tomorrow we'll pick up whatever we need to review. And then we'll be testing on Friday. These are some more perpendicular bisector ideas. The constructions are actually these very last ones. So on these last three, those are the ones you need the tools on. If you would like to start there, use your tools, and then not have to mess with it later, that might be a good idea.